Hey guys, here's the first video in a series of a couple of videos that we're going to do on thermodynamics and enthalpy. So in order to understand thermodynamics and enthalpy, we first have to understand energy, right? So we talked about it before. Energy is basically the ability to do work. We talked about it in the last unit in terms of activation energy, but we're going to focus a little bit more on the specific energy we're going to be working with. Okay, so let's take a look at the formula for kinetic energy, because that's how we perceive energy, right? Motion. So kinetic energy is equal to 1/2 mass times the velocity squared, which is what we see here, right? Now, if we were to, for example, get a mass that was 2 kilograms moving at a velocity at 1 meter per second, right? Let me see, why is this so thick? 1 meter per second, then we would replace the values at 1/2 is equal to 2 kilograms times 1 meter per second squared. If we substitute the values, we're going to end up with 2 kilograms times meters per meter squared over second squared times 1/2, which gives us 1 kilogram meter squared over second squared. Now, this unit that we have here represents the joule, okay? The joule is the accepted unit for energy. 1 joule equals 1 kilogram meter squared per second squared. Now, a joule is not a whole lot of energy. So when we deal with the amount of energies that we're going to be working with, we want to make sure that we have numbers that we can manage easily. So in this situation, what you're going to see a lot of is kilojoules. 1 kilojoule is equal to 1,000 joules. So when we work in problems, or for example, when we're doing activation energy, you'll remember that the unit that we saw on the activation energy chart, which kind of looked like this, right, was kilojoules per mole. All right, kilojoules, sorry. Okay, so we're going to be working with kilojoules pretty often. Now, when we're talking about energy in a system, right, we're talking about heat. You know, energy, one of the byproducts of energy being absorbed into a particular system is heat. So heat is measured in calories. 1 calorie equals 4.184 joules, right? And like the joule, the calorie is not a huge amount of heat. So just like the joule, you're going to also see 1 kilocalorie, which is the same thing as saying 1,000 calories. Now, these can go back and forth between joules and calories. So when we're talking about 1 kilocal of heat, that equates to 4.184 kilojoules of energy. Now, off to the right, you're going to see a little table there that's going to come into play here in just a minute. But how does energy and heat relate to one another? Well, we can go back and forth between energy and heat because the amount of heat that is absorbed by a particular substance can help us determine the amount of energy that was introduced. So by measuring the amount of heat, we can actually calculate the amount of energy. Or if we can measure the amount of energy, then we can calculate the amount of heat. So both of these things kind of work hand in hand to help us determine one or the other. Now, how do we do that? How do we introduce heat, right? How does that transfer to energy, right? And that has to do with the table that we see here on the right. Every substance on Earth has an ability to absorb heat. Some substances absorb heat in a much easier way. Others do not. But the ability to absorb heat allows us to determine the amount of energy that is either being absorbed or displaced in the system by looking at its ability to absorb heat. Let's take a look at the table that we have here. So if you look at the table, we have several different substances: carbon, copper, ethanol, gold, granite, etc., etc. And you're going to see that there's values that have to deal with its specific heat. This is the amount of energy needed to raise 1 gram of the particular substance by 1 degree Celsius. So if you take a look here, this is represented as both joules per gram Celsius and calories per gram Celsius. So what this is telling you is this is the ability of this particular substance's ability to absorb heat to change the temperature of that substance by 1 degree Celsius, right? So you can see that the different substances have different abilities to absorb heat. I want you to pay special attention to water, which is right here, okay? I want you to take a look and I want you to notice that water has a huge specific heat capacity, which means that it takes a lot of energy to change the temperature of water. And we'll see why that plays a role a little bit down the line here. Now, let's focus on specific heat because we just reassured ourselves that we can use the amount of heat absorbed by a substance to determine the amount of energy present, right? Or the amount of energy absorbed. So how do we do that? Specific heat can be expressed in using this equation. The specific heat of a substance is equal to the amount of energy absorbed divided by the mass in grams times the change in temperature, right? So using this simple formula, we can either determine the specific heat of an unknown substance by measuring the amount of energy taken, or we can use unknown specific heat to determine the amount of energy that's being absorbed using its ability to absorb heat, okay? Now, the units for specific heat can be either in joules, as you can see here, joules divided by grams Celsius, or calories per gram Celsius. It can go either way, and if you look at the table, it is both in joules or calories. So depending on what you're working with, you'll be able to use joules or calories so you can get the correct final unit. All right, let's take a look at a practice question of how we can use the specific heat to determine how much energy has been absorbed by a particular substance. Okay, so the question says, a gold ring with a mass of 5.5 grams changes temperature from 25 degrees Celsius to 28 degrees Celsius. How much energy did it absorb? Now, in this situation, we have the mass, which is 5.5 grams. Okay. And we have the change in temperature. So if you look at 25 to 28, you can see that the change in temperature is 3 degrees Celsius, right? Now it's asking you how much energy did it absorb? Okay, so we have to set this up and we have to solve for energy absorbed, right? Now, we're working with gold. So this is gold right here. If we take a look at the table, we can see that we have the specific heat for gold. It's right there. This particular question is asking us for the amount of energy absorbed. In this case, there's no specific one, so we can either use the 0.129 or we can use the 0.0308. In this case, let's go ahead and just keep it in joules and we'll see what we come up with, all right? So if the specific heat is equal to the energy absorbed, okay, and then we divide that by the mass and the change in temperature, right, which is represented as delta T. Then all we have to do is solve this equation for energy absorbed. Now, in this case, what's in the denominator is the mass and the change in temperature. So if I multiply both sides by mass delta T, right, they should cancel here. And then this is mass delta T, so it's a little tight there. We should end up with the energy is equal to the specific heat of the substance times the mass of the substance and its change in temperature, right? So in this case, all we have to do is plug in our values. So let's take a look. Energy is equal to the specific heat. We already determined that was 0.129 joules per grams degrees Celsius. And if we multiply that by the mass is 5.5 grams. And if we multiply that by the change in temperature, which is 3 degrees Celsius, then we should get our answer. Now, in this situation, we're working with joules. So when I multiply grams in Celsius, what you're going to see is that these guys are going to cancel. When these guys cancel and you multiply everything together, you're going to end up with 2.1285 joules. Okay, now if we round that, we can round that to 2.1 joules of energy absorbed. So by looking at the amount of energy, or by looking at the amount of the specific heat or its ability to absorb energy, right, or heat, then we can determine the amount of energy that was absorbed by the system. In this case, the 5.5 grams of gold changed temperature by 3 degrees, which means it took 2.1285 joules of energy to change that amount of gold from 25 to 28 degrees. So once again, the relationship between energy and specific heat allowed us to determine one or the other, right? In this case, the energy absorbed is 2.1 joules. Now, when we're working with specific heat, right, and the ability of different substances to absorb energy, what we're really talking about is the thermal properties, right? Now, there's a couple of things that we need to look at. So heat capacity is the amount of heat, here, is the amount of heat that must move into a substance to change its temperature. By 1 degree. Okay. When we're talking about molar heat capacity, then what we're talking about is the energy needed to raise the temperature of 1 mole of a substance. By 1 degree. Okay. Basically, the unit ends up being that you have 1 over grams times, 1 joule times the molar mass of a substance. Now remember that molar mass is equal to grams per mole. When you multiply the heat capacity, right, or the specific heat by the molar mass, then you end up in joules per moles Celsius. And if you're talking about just the mass, which is what we have in heat capacity, you still end up with joules over grams degrees Celsius. When you multiply that by just the mass, which is in grams, then the mass cancels, the G's, and the heat capacity is left as 1 joule, right, over degrees Celsius, right? Now, just like before, remember that this can be in joules or it can be in calories. Same thing here. This can also be in calories, which is moles degrees C. Okay? The heat capacity and the molar heat capacity of different substances will be determined specifically by either their mass or their molar mass if you're working with a compound. So let's take a look at a sample question here. So a sample question says, how many kilojoules can 250 grams of water absorb for each degree Celsius change in temperature? So basically what they're looking for in this case is just the heat capacity, right? The heat capacity of water. Now, in this situation, right, we're going to use, let me go ahead and get this one. We're going to use the specific heat of water, right? So let's take a look. Let's scroll up here and let's see what the specific heat of water is. In this case, the specific heat of water is 4.1796, right? So 4.1796. This is joules per gram degrees Celsius. Okay. And remember what we said, it's going to be just times the mass. So we're going to multiply this by 250 grams of water. Right, and then what's going to happen is grams are going to cancel. We're going to end up with 1.045 joules per degree Celsius, or you can write it as 1.05 times 10 to the third joules degrees Celsius. Okay, so in this case, measuring the heat capacity of water at a specific amount, in this case 250 grams, we're able to determine that it has a heat capacity, or that amount of water has a heat capacity of 1.045 joules. Okay, all right. Now, all this relates together because water is one of those things that we can use to measure the amount of energy or heat being absorbed or released. Now, I want you to pay special attention to the amount of the heat capacity between water and iron. And iron is right here. Okay, so you can see that by comparing these two, this is almost a tenfold increase, right? Water has a huge amount. This is almost 10 times, right? Huge amount of ability to absorb energy. And water's ability to resist change, or using a lot of energy to resist change, is what allows people to maintain homeostasis, for example, right? That's why we're able to adapt to live kind of all over the place, because since we're 60% water, the water's ability to resist temperature change allows us to maintain a more constant temperature within our bodies. And water is one of those things that we can use because it resists change, right, to determine the amount of energy either being absorbed or being released by a system. Now, thermochemistry, right? Thermochemistry has to do with the transfers of energies between reacting chemicals. Okay, reacting chemicals. In order for us to understand how thermochemistry is going to be measured, or how we're going to understand it, we need to lay down a few ground rules. Okay, so one of the first things we want to talk about is a system. Okay, a system is something, the thing that we're studying, right? So it's whatever we're studying. We are studying. Now, whether that's a chemical reaction happening in a flask, or if it's the energy transfer happening inside of a battery, the system is specifically what we're studying. Okay. Around the system, right? So let's say we have our system is a flask, right? So I'm going to draw a flask here. And we have a chemical reaction going on inside of this flask. Okay, so inside, right, the reaction here, right, inside is what we call the system. okay? Everything around the outside, right? Everything around here is called the surroundings, right? And what we're measuring is how the system affects the surroundings, because what we're measuring is actually the system or the chemical reactions effect on its surroundings. So pretty much everything outside of the system is called the surroundings. Okay. Now, between the system and its surroundings, we have the boundary. And the boundary is what separates the system from its surroundings. Okay? So the boundary it exists as a barrier between the two. Now, sometimes that barrier is insulated and other times it's not. An insulated boundary isolates the system from the surroundings, right? And an uninsulated boundary allows the system to directly affect its surroundings. Now, the state of the system, right, is it's basically a listing of its temperature, its pressure, its volume, its composition. Basically, how we have the system as it's happening. Any change to that system, right? Whenever any change occurs, then we call that the change of state of the system. So what we're measuring then, right, is how the system is being changed and by how much. Now, when we're talking about a system and its ability to affect its surroundings, then we're looking specifically at the heat of the reaction. The heat of reaction, okay? The way the system changes depends on whether energy is being absorbed by the system or being released by the system. So there's two basic changes to a system, changes of state of the system. When energy is being absorbed, by the system, we call that an endothermic change. Okay, and we talked about this before. When the energy is released by the system into its surroundings, we call that an exothermic change. Okay. In an endothermic change, right, we notice in the surroundings, because remember, we're measuring the surroundings, we see that heat, which is represented by Q, right, will have a positive value, right, because it's absorbing energy, right? When we have an exothermic change, we're going to see that the amount of heat or the amount of energy on the system is going to have a negative value. Because remember, if there's energy moving out of the system into the surroundings, then the system is losing energy, which means it's going to have a negative value. The surroundings are gaining energy, but it's being released by the system. So in this case, the system loses energy, right? In an endothermic reaction, the energy is actually coming from the surroundings and going into the system. So in this case, the system gains, which is why you see a positive value, right? This is going to be counterintuitive to what we said before, but remember that when we're measuring the amount of heat either being absorbed or released, we're talking about the amount of heat absorbed or released into the surroundings. So even though the system is losing energy, we perceive that as heat in its surroundings because now the energy is out of the system and into the surroundings. So we perceive that as a gain in temperature or a gain in kinetic energy, right? Because we're in the surroundings. If a system is gaining energy, then it's going to pull from its surroundings, go into the system, which is what's going to be perceived by us as a net drop in energy in the surroundings. So remember, when we're talking about the endothermic or exothermic, we're talking about what's happening inside here, the system, right? Everything else on the outside is not the system, it's the surroundings. All right, so we'll stop there for now, and then we'll pick it up here in the next video.